name is William, and today we're going to be talking about self-driving cars. Now, with companies such as Tesla commercializing self-driving cars, the issue of public road safety has become a rising topic of discussion. To address this issue, my research focuses on developing an autonomous vehicle framework that handles automation to automation and human to automation interactions. Well, how can this be accomplished? Let's talk about reinforcement learning and game theory.
Reinforcement learning is the concept of learning a behavior based on rewards. In my research, I'll be using a reinforcement learning algorithm called Deep Q network, which uses a neural network to learn from the environment. The reason for choosing this algorithm is because it has found success in the Atari gaming environment, where it achieved professional gamer status. However, reinforcement learning alone is not enough to accomplish our task. Let me introduce you to the Level K theory. The Level K theory is a game theoretic model that allows individuals to act based on their predictions about others' actions, where the main individual is level K, while others are level K minus 1. Take the game rock, paper, scissors as an example. If the average person, level 0, plays scissors first, a level 1 player assumes that everyone else is level 0 and will play rock in order to win. In my research, I use this theory to allow my self-driving car to predict the actions of other drivers.
Now with the Deep Q network and the Level K theory, I am well on my way to accomplishing my goal. But I'm still missing one key component: the environment I want to experiment in.
In my research, I decided to use OpenAI Jim's highway environment, where I specifically focus on the 4-way unsignalized intersection. To start my research, I needed to alter 3 major features in my environment: the number of vehicles, the objective of the simulation, and the input received by the self-driving car. First, I modified the number of vehicles to 3, which simplified the scenario. Secondly, the objective was modified to complete the intersection, which decreases the simulation time. As you can see here, the simulation ends once the vehicle reaches the opposite lane. Last but not least, I created 3 discrete categories representing the opponent vehicle's distance, direction, and motion from the self-driving car we are training. This provided a realistic representation of data we could collect using sensors. For distance, the value calculated can be categorized as close, nominal, or far, which are represented as 0, 1, and 2 respectively to allow for easier processing by the neural network. Moving on, the direction was calculated through finding the angle theta in respect to a predefined plane. Using the angle, the value is categorized into one of the 8 sectors as shown. Lastly, the motion was calculated through using the distance's historical data. If the distance increased over time, then the motion would be defined as moving away. If it stayed the same, it would be stable. If it decreased over time, it would be approaching. After piecing everything together, the self-driving car is ready to be trained. To start, we need to train the car to adopt a level 1 and level 2 strategy to represent vehicles that our self-driving car will interact with. A level 1 car represents a passive vehicle that moves slowly before the intersection. A level 2 car represents an aggressive vehicle that proceeds through the intersection without stopping. During the training process, our self-driving car has learned 2 strategies: a passive strategy to interact with aggressive vehicles and an aggressive strategy to interact with passive vehicles. Using these learned strategies, we can train our vehicle to achieve an adaptive control strategy. To achieve this, I've constructed 2 neural networks. The first neural network predicts if the current scenario is critical to determining the opposing vehicle's levels. If yes, the second is used to predict the level of the opposing vehicles based on the environment's input and their actions. Otherwise, the car will assume they're level 1. Take a look at the results. When interacting with 2 level 1 vehicles, our vehicle is able to predict that the other vehicles are level 1, which allows it to deploy a level 2 strategy to proceed through the intersection safely.
Now, with these results, we can use game theory and reinforcement learning to create a framework that allows for a vehicle to interact with multiple different types of drivers. However, despite this success, we still need to consider a lot of things, such as what would happen if we added more vehicles, or if we changed the destination of our vehicle. These are the things that we need to consider before truly calling this a success. Nevertheless, This was still a milestone and can prove to have a significant impact on current research, as current research focuses on deploying game theory with decision trees. However, this can be computationally intensive as scenarios become more complex. And this is where reinforcement learning comes in. Reinforcement learning requires less resources, thus will become less computationally intensive. And this will be more feasible to implement in innovative technologies such as self-driving cars. Overall, I hope you guys learned something from my presentation and you enjoyed it. Alright, see ya.